In this week's superhero simulation, we're going to be looking at Autodesk Simulation Mechanical to do a steady-state heat transfer analysis of the X-Men Cyclops Visor. If you have any questions, as always, feel free to reach out to me at james.herzing@autodesk.com, ping me on Twitter at Mr. Simulation Rocks, or hit us up directly at the simulation Twitter handle shown. So we all know who Cyclops is if we're watching this. He's the kind of tool bag leader of the X-Men, shown right there in the blue. But what I'm really interested in is that fancy visor that he's wearing. And he shoots a laser out of it. It has to get hot. So how hot is that laser, and how can he keep it on his head for so long? So I know I've seen him cut through steel with this thing, so I thought that would be a good starting point for me. So I thought an acetylene torch, the most common fuel for cutting steel, reaches somewhere around 3,500 degrees C when cutting. And I'm told the average is about 3480. One note, the visor is told to be made out of ruby quartz, which is probably some fancy material that doesn't really exist, so we're going to have to factor that in a little bit. Alright, so to start, let's just open up a step file in Simulation Mechanical, and then apply a mesh. To do that, you just click the Generate 3D Mesh button. As a note, we could be doing this in Simulation CFD or in Nastran InCAD as well. So with the part meshed, we're now going to be able to apply our loads and boundary conditions to the model. So we're going to start by selecting some surfaces, and we're going to pick all of those surfaces that Cyclops is going to be shooting that big red laser out of. And with those selected, we can then right-click and choose to add the condition we want. So this time we're going to use a surface-controlled temperature and define it to be 3480 with a high stiffness value. So what this means is, pretty much no matter what we do, that surface is going to remain at that constant temperature. The higher the stiffness, the harder it is to change that value. So we know that laser shooting out of there, it's going to be pretty warm. So now we're going to give Cyclops the benefit of the doubt here and assume that somehow he has some sort of cooling going on in the area that it's strapped to his head. So around like those ears area, we're going to go ahead and again define another surface controlled temperature, and this time we're going to define it to be a little closer to room temperature, and I don't know, put in like a 22 there. And again, this will show that these temperatures in that area are going to remain cool. So just assuming that this thing is made out of some technology I don't really know about, it's going to stay cool there. But let's see how much the rest of it heats up. So next, let's go ahead and define our materials. So if we go and edit material, we can see what we have to choose from. So no ruby quartz listed here, but we do have quartz of some sort, fused quartz. So let's just assume these properties are relatively the same, because I couldn't actually find material properties for ruby quartz. And go ahead and click OK. And lastly, we're going to go into our analysis parameters and set up the multipliers to make sure everything is active when we're running our analysis. We're going to define a default nodal temperature of 20 degrees C, and then we're going to be ready to solve. Now keep in mind, this setup is the same for any steady-state analysis that you're going to be running, be it Cyclops Visor or something a little more realistic. So let's press Analyze and quickly get to our results. So here you have it, the meshed results of the visor, where we can see that in the area that the laser is shooting, it's still up around the 3,500 degrees C area. The ears are still around 22, but even in the other parts, we're looking at something in the range of 15 to 2,000 degrees C. This says to me that this is going to melt poor Cyclops' face off, or at least blow up the metal that it's made out of. So I think the X-Men need to give us a little more detail about what this is actually made out of. If you do have any questions, comments, concerns, or information that I'm missing about this great design of his visor, please let me know, and I'll be happy to take that into consideration in the next analysis.